We are studying Hooke's law, and Hooke's law is defined by the equation force is equal to negative k times our change in x. So what does this mean? Well, I'm going to get into that here, but first, let me draw a little diagram of what you can use for this equation. So if we have a spring with no load attached to it, and we measure it out, and it's 5 centimeters, make that look like an M. So our spring is 5 centimeters from bottom to top. That's in the state of equilibrium for the spring itself. But if I attach a load to it of, we'll do 500 grams. But we see that attaching a weight to the spring has extended it by another 2 centimeters. So now the spring has been stretched out from here to here, and it's had a change of 2 centimeters. So what does that mean? That 2 centimeters is actually going to end up being our value for delta x. So let's go over the Hooke's law equation. The force could really be called the force of restoration. I'll give it a subscript r just to differentiate it from other forces. So the restoration force is equal to, let me just write out the name. And then our k is the proportionality constant. Now this is an interesting value here, this k, because this applies directly to the strength of the spring that you are using, that you're applying the equation to. But our delta x is our displacement. And in our case, the delta x would be 2 centimeters, because that's the amount that the spring has changed in length. That's the amount of displacement. Okay, so let's get back to the proportionality constant. K will be big for a big spring. So if you have a larger value, then you have a stronger spring. If you have a smaller value, then you have a weaker spring. So let's see how that works. So we have some givens in this problem. We're going to need a few more numbers. We're going to need our gravitational constant. That's going to be 9.8 meters per second squared. And we'll make that negative because it's going to go the opposite way of the spring. We're going to need to convert our mass. So right now we have a mass of 500 grams. But we're going to convert that to kilograms. So that's going to be 0.5 kilograms. Why am I converting? Well, it's because I'm going to be working in newtons and meters. So I need to do some unit conversions ahead of time. And then we have a displacement over here of 2 centimeters. So our delta x is 2 centimeters. But what does that translate over to? That's 0.02 meters. So let's just see what the forces are doing. Right here, we've got a 500 gram weight, but it's being pulled down towards the ground by gravity. So we've got our weight, and it's going to be in the negative direction because it's going away from the spring. We have this spring applying a force that counteracts the weight, and that is going to be our restoration force. So that's the force that we're talking about here in Hooke's law equation. Okay, so let's do some plugging in. So we see our equation, we've got force, and then we've got our spring constant, we have our displacement as well. But that doesn't really look like the numbers that we have to work with. So we're going to have to use some of these to derive the force. So we can derive the weight force by using our good friend weight equals mass times gravity. My weight, I'm just going to call it the force having to do with weight. We already know what the mass is. I'm going to put my kilogram converted mass. I'm going to multiply it by gravitational acceleration of negative 9.8 meters per second squared. So this will give us the force due to the weight. It's going to be negative, and that's fine. So when we calculate that all out, we've got 0.5 kilograms times negative 9.8, and we get a force of 4.9 newtons. Okay, but it's negative because of our negative gravity. So that's our force for our weight vector. That's this one over here. Okay, we know that there's no acceleration, and then there's no velocity happening once this weight stabilizes. And so we're at a point of equilibrium once the weight has been added to the spring. So it's going to stay stretched out that extra 2 centimeters and just stay still at that point. So what we could do knowing that is we can take the equal and opposite value of our weight and apply it to our Hooke's law up here for this restoration force. They'll be the same because there's no acceleration going in either direction, right? So therefore, we can make our our restoration force the same magnitude, 4.9 newtons, but it's positive because it's going in the other direction, right? It's opposite of the weight. Okay, with that in mind, let's try to plug all this into the Hooke's law equation. So we've got our 4.9 newtons over here on the left side, and we've got the negative k, we don't know what that is yet, times our displacement of 0.02 meters, and I got that when I converted my centimeters over here. And we know that that's in the opposite direction of the way the spring goes. It's the same direction that the weight force is going, so that has to have a negative sign on it as well. Okay? Because our displacement is actually a vector. So what does that do to this side? Well, negative times a negative is a positive, so that makes this whole side positive. So what we can do then is we can isolate the k. Now it's going to be a positive k, and I can divide it by 0.02 meters. And that will give me a unit of Newton meters for my answer, and that will give me 245 Newton meters for my answer. So that is equal to my k value, my spring constant for this particular size of spring. Now, what if we were to compare this, and I'm just trying to show you what would happen if we had a different size of spring but the same situation. Okay, so I'm going to keep everything the same except for my delta x here. My new delta x is only going to be 1 centimeter. So maybe I have a big thick spring and my 500-gram weight is not going to stretch it out that much. Okay, because it's a stronger spring, so there's less displacement. I'm just using easy numbers to show you what happens with the k value. So we still use our weight equals mass times gravity. Weight equals mass times gravity. And we find the same forces acting because it's the same size of weight. So our force for our weight is negative 4.9 newtons, and therefore our restoration force is going to be the same, except positive. Okay? So, because that is directly related to the weight. So that's why these things aren't changing at all. So what we get is we're going to find a different k value based off of our displacement being smaller. Instead of having 2 centimeters of displacement, we're going to have 1 centimeter of displacement. So let's plug things in. 4.9 newtons for our restoration force is equal to our negative K times negative 0.01 meters. That's for that 1 centimeter. Okay, so let me just label this bigger, stronger spring. New delta X is 1 centimeter. Just so things will stay straight here. Again, negative times a negative is a positive, but we end up with our 4.9 newtons divided by 0.01 meters. So that is going to be equal to our K. So we just divide all that out, and that ends up being 490 Newton meters. So that's a bigger K value right there. And that is reflective in the smaller displacement because a bigger spring doesn't stretch as easily.